Okay, now the remaining examples are from your workbook. So this is friction example 1. We've got Luigi pushing a 95 kilogram filing cabinet at a constant speed across the floor with a force of 196 newtons. And we want to know the coefficient of kinetic friction between the filing cabinet and the floor. Well, because we have a constant velocity, we know the F net is 0. I have no acceleration, so my acceleration is 0. And as a result, I know that my sum of the forces in the x is equal to my applied and friction, and they have to cancel each other. So if my applied force is 196, my friction force is negative 196 in the opposite direction. Now similarly, when we look at the vertical forces, gravity and normal are opposing each other, and they cancel each other out. So we know that the normal force is equal to the negative force of gravity. So what I can do is I can substitute these values into my coefficient of kinetic friction formula. So I know my friction force, I know my normal force, and we get a value of 0.21. So therefore the coefficient of kinetic friction is 0.21 between the cabinet and the floor. I do want to point out that we did have some negative numbers here, but we ignore them when we write the final answer for the coefficient of friction. The coefficient of friction is always an absolute value. It's always positive. Now, this is example 2. We've got Karina pushing her desk with a force of 120 newtons. Now, this is a little different because now the desk is actually accelerating at 0.85 meters per second squared. So we want to first figure out the force of friction acting on the desk, and we want to know the coefficient of kinetic friction between the desk and the floor. So drawing a free body diagram, what we know is that the desk is accelerating at 0.85 meters per second squared, and we'll see it forward is going to be positive and up will be positive. So I know my F net is forward. I know that my gravity and normal are going to be opposing each other. So if I know my gravity force, I know my normal force. So what we're going to do is we're going to first find the net force acting on her room. Then once we know the net force, we're going to be able to find the force of friction from the free body diagram. And once we know the force of friction, we can substitute it into the coefficient of friction equation and determine our coefficient of friction. So go back. Let's find the F net. So I know we have an acceleration, so I can determine my F net. So my F net is equal to mass times acceleration, 95 kilograms times 0.85 meters per second squared. And we get one of 80.8 newtons. So that's my F net as acting forward. Now to find friction, we can use our free body diagram. I know that the sum of the forces acting the x are going to equal to friction plus my applied force. Here I know that my F net is equal to the Fx, overall Fx force, 80.8 newtons. I know my applied force was 120 newtons forwards, so my friction force must have been acting backwards at 39.2 newtons. So I've got my friction force. So I'm going to take that friction force, substitute it into the equation, along with the value for the normal force at the bottom here, which we found was 932 newtons. And you plug it in, you get a value of 0.042 newtons. And again, like before, we ignore the negative signs. The coefficient of friction is an absolute value. So therefore, the coefficient of kinetic friction for the desk and the surface of the floor is 0.042. Again, no units. Now the last example, we have Surfing Bob driving his dune buggy at a speed of 54 kilometers an hour on a beach where the coefficient of kinetic friction is 0.3. We're going to want to figure out the force of friction and then how long it's going to take the car to come to a stop. So what we're going to do, we're going to draw a free body diagram. Step 1. Then we're going to use the coefficient of friction to get the force of friction. We're going to determine the net force acting on the dune buggy, the acceleration, and then finally from the acceleration we're going to determine the time. So that's kind of the game plan we're going to be using. Okay, so what we've done is we've done some work here. First thing I said we were going to do is draw a free body diagram of the vehicle. So we have all the forces acting on the dune buggy. We have gravity, normal, and force of friction. It does mention that the engine stops working, so we have no applied force. We don't have to worry about that. So we calculate the force of gravity. We know that the normal force is going to be equal and opposite to that. I also know that the coefficient of friction between the dune buggy and the sand is 0.30. So knowing that, we can substitute into the coefficient of friction equation and solve for the force of friction. So just going to rearrange the equation, and my force of friction is going to be 0.3 times my normal force, which is 14,715 newtons. And this gives me a force of friction of 4,400 newtons. And it's going to be acting backwards. I manually have to put in the negative sign in here to indicate that's going backwards. Now, once I've done that, I can determine from the free body diagram the fact that the net force acting on the dune buggy must be because of the friction force. So F net is equal to force of friction is equal to negative 4,400 newtons. Then I can use this value in my F net equals ma equation to get my acceleration. So get an acceleration of negative 2.93 meters per second squared, which makes sense. We're accelerating backwards. We're coming to a stop. And then we're going to use that value to determine how long it takes to stop the vehicle. So the vehicle, the dune buggy, is traveling at 54 kilometers an hour or 15 meters per second. So don't forget the conversions. It's going to come to a stop. I know my acceleration is backwards because of the friction. And I want to find the time. So the appropriate equation is our basic acceleration one, a equals v2 minus v1 over t. We rearrange to get t equals v2 minus v1 over a. Substitute our values in, and we're going to get a time of 5.11 seconds. Now be careful here. Make sure that your acceleration is negative. If you forget that, you're going to have a negative time, and that's not possible. In our final statement, we've got to just check for significant digits. It looks like we've got 2 significant digits here. So my final answer should reflect that. So my final answer should be the car will come to a stop after 5.1 seconds. So only 2 significant digits here. It should be 5.1 seconds. And that's it. So I'll be assigning you some problems to, to keep you entertained. Have fun with them. And we're basically done the unit. Just going to do a few more review problems. Bye.
Bye-bye, physics people.